Hello everyone. I'm going to start a series of structure analysis, question and answers. So the first question today we're having is of a beam that has both ends that are fixed. And as you can see, this is the first question. I'm going to record more of this and also post it to my YouTube channel. So don't forget to like and subscribe to follow up this more. First of all, to start with, if you're to see the far ends of this beam are all fixed. They're all fixed at an equal distance of 5 from the middle support, which is a hinge. And there are two forces here. We have one which is a UDL, which is 24 kilonewtons per meters. Then we have the 50 kilonewtons. And it's not uniformly distributed point load. It's at a center of a distance of 2 and 3. So the first step to analyzing this kind of a beam is to find the fixed end moments, whereby we're going to divide this using spans. The first span we're going to work with is span A to B. As you can see, well, I found the fixed end moment of A to B and also the one from B to A. And according to the way the arrows move, this one is a negative because it's in the clockwise direction, and this one is in the anti-clockwise direction. So when you find them both, this one is 36 and this is 24, but this one since it's in the clockwise direction, it's negative. That's well represented here. Same applies to this side here. But then take note, if it is a point load and the distances from it are different, you're going to use this. If the distances are equal, we have a formula we're going to use, which I can't show for in this video, but in my next video I will get a question which reflects to that exactly. So that is span AB. Then the span BC, which has the UDL of 24 kilonewtons per meter. This is how it's distributed along a span of 5 meters. So we're going to find the fixed end moment from B to C and then from C to B, where B to C is negative, so we're using the negative WL squared over the 12. And then for the CB, we're using WL squared over 12. And the values have been found here. So we're going to find a stiffness. And the stiffness, for us to find it, which I represent using K, stiffness K. So stiffness K from BA and BC. And the reason why we're representing using BA and the BC is because for you to find a stiffness, it has to be at a joint. For you to find a stiffness, you have to use the one that is from BA and BC, since B is the joint where it has two members, that is BA and BC. So I found the stiffness at BA and also at BC, and it's the 4EI over the L. Since the far end at B, they are both fixed. If it was a hinge or a roller, it wouldn't be what? It wouldn't be a 4. It will be a 3 over 3EI over L. L is the distance. Take note of that. L is the distance. After finding the stiffness, we're going to find the distribution factor. The distribution factor is going to be found at the joint. But in our question, we only have one joint, and the joint is at B. So, and we have two members, that is BA and BC. And we had already calculated the stiffness, so we're going to find the total stiffness, which is here, and we'll find the distribution factor, which is represented by dF. And make sure that each time you're working at a joint, the distribution factor at that particular joint has to equal to 1. If it does not equal to 1, then you have calculated it wrongly. And also, sometimes Sometimes for a roller or a hinge support, especially if the far end is a roller or a hinge support, the distribution factor will be equals to 1. So we're using the moment distribution table. So we're using moment distribution method, because there are two methods to be used here that I mainly use: slope deflection and moment distribution. Those are the first two we're going to be working with. But for now, let's first work with moment distribution before we go for those other remaining 3 methods. But for now, let's work with moment distribution. So we're going to manipulate these values and using the moment distribution table. So the first thing you do to be organized, write the joints, and the joints here there's A, B, and C, because those are where the supports are. So the members in in each joint, we have AB at A, and BA at B, and BC at B. There's also CB. So when you're calculating this, when we calculated this, remember the distribution factor, it happens at a joint which has other members, and we don't have it for A and at C, so they are represented by 0. You're going to represent your distribution factors, put them there, and after that you calculate and you represent the fixed end moments, then you balance and distribute that and carry over moments. But then also for you to calculate this, you have to add 24 plus negative 50, and that negative 50, when you add it, it will give you a value of, let me show it for you here. It gives you this, no, I've calculated wrongly. It's supposed to be 24 plus negative 50, which gives you negative 26. But then for you to represent this, the best way, there are two ways different people will express this. Others will say for you to represent that in this balance and the distribution factor, you have to divide this negative 26 by 2. When you divide it by 2, this is what you get negative 13. But then for you to represent this on the balance, it has to be written as the opposite sign of what you found here. So you represent this here and the 13 here, which are already positive. And since you didn't find any distribution factor along this column, here it becomes 0, and here it also is 0. So for you to be able to carry over, you divide this by 2 and represent it here, and also this side. Since it's a 0 here, it becomes here 0. This one is 0, it comes automatically here 0. When you divide this, it gives you 6.5. But remember, the sign you carry, the sign conversion you carry here for the carryover moment has to be the sign that is here. So you write all of that, at least work 4 iterations. That's what I'm suggesting. 4, then, so that you represent the final moment, which you're going to add starting from the fixed end moments up to the last balance and distribution. When you add all of that, then you represent it for each column. You do the same. So after you've worked with the moment distribution table, you work out the support reactions. And remember, for the support reactions, for you to do this best, you can represent all these values that you had found from the moment distribution table onto the diagram. The diagram of the beam. Represent all of them and ensure that these arrows are well drawn, and these arrows are drawn based on the signs when you do the final moment addition on the table. So as you can see, I've represented it here. You have to find each moment and find the support reactions. I think this is basically strength of materials. Now this part, you can go back to your lectures of strength of materials, but then also if you're a bit having an issue with that, you can still find that by taking off moments. For example, here I took at A to find RB1, which I represented here. Then you also then you add the RA reaction RA plus reaction RB1 equals to 50. This is according to the vertical forces being equal to the opposite verticals. So it's here. You also work the same for span B, but remember this is a UDL, so you have to multiply it by 5, which is the total distance here times a half of that 5. So you find the RC, and then you take the same to find RB1, and when you add the total reactions at B, RB1 plus RB2 equals to RB. So you find this, then you represent them outside, then you continue to work on the shear force values. So when you work on the shear force values, remember the shear force at A equals to 0, and the one before A is 0, since it's a fixed point at A. So you're going to find the one immediately after A, which is 28.5, since that was reaction at A. And you do the same in these other values. As you can see, you use these values, make sure you carry out them the right way so that you can be able to plot a correct shear force diagram, which is well represented here. Though some people would prefer to draw the shear force, the end force diagram, the free moment diagram, and the bending moment diagram in one sheet. I prefer not to do that. I prefer to do mine separately on each sheet. So this part is the one for the free bending moment diagram, which is the FMD. You have to find the free moments at the span of AB, which are found here. It is 60, which is a positive, and the one at BC, which is where the UDL is, and it's here 75. So this is the graphical representation that I have for it. And make sure to check your signs very well, because you can write a wrong sign and doesn't give you good marks. So we have also the end moment diagram, which is literal a negative. I just didn't present it here well, but yes, it's here. These values are the ones you got from the table, the moment distribution table. You present them. Then for you to find the final end moment diagram, you combine the end moment diagram and the free bending moment diagram. When you combine them, you shade the lines that are above and mixed up like this. You shade them, and the shading which is below this line, they all are represented in negative, and the ones that are side are in positive. And this is the final working for the solution. Please don't mind my grammar. I'm not very good in speaking English, but I hope to improve in that. So don't forget to like, subscribe, and comment. You can raise to me your questions, because I also love to learn. I'm just a student. I learn to love to learn. I love to learn, and I will also appreciate it if you're willing to drop for me guidelines on how to improve my content. Wish you all the best.